Hello, my name is Dr. Edward Fisher from the University of Edinburgh, and this short tutorial is about how to detect single photons using avalanche gain in silicon. One of the things that we would like to do as metrologists is to look at very low levels of light, including single photon levels of light. So some of the applications that we're looking at are things like light detection and ranging LiDAR systems for ADAS systems of self-driving cars, as well as free space and fiber optical communications. Of course, we also use single photon detectors and the detection of low-level light for astrophysical observations using adaptive optics, as well as using image sensors for photography, as well as space and Earth spectral imaging. Some of the biomedical applications that we use light detection for are things like endoscopy, where you would like to look inside the human body, as well as spectroscopy using Raman spectroscopy for chemical analysis, as well as pulse oximetry and a technique called cranial near-infrared absorption spectroscopy that allows you to look at oxygenated and deoxygenated blood within the brain. Some of the more modern usage of single photon avalanche diodes is positron emission tomography and fluorescence microscopy. So of course, the question is, what is a photon? Well, from a philosophical point of view, you could either take a realist or anti-realist stance. A realist would say that the photon is a real particle and that the wave version of light is a real wave. They would also say that the quantum theory, is the absolute way that the physical, real, natural world is working. Anti-realists, on the other hand, would say that the photon is not real, and likewise that the wave is also not real. They would say that these are just conceptual models, a way of aiding our understanding and a way of communicating linguistically between each other, and of a way of thinking about a scenario. In fact, if a theory is falsifiable, they see it as our best guess at the way that the natural world is working. Stephen Hawking proposed a slightly different idea, and that is of model-dependent realism, where both the photon and the wave are real entities or could be viewed as real within the remit of what those models do. He suggested that both are valid theories, both are falsifiable, but that you use the correct model for the situation that you need to use. There's a little bit of further reading here on that. So where did the word photon come from? Well, we heard a lot that Einstein theorized and provided the theory for the photoelectric effect in 1905. However, the current form of the word photon was coined by Professor Gilbert Lewis in 1926 in a Nature paper. However, the word photon is a little bit older than that, around about 10 years, and it was coined by a chap called Leonard Trolland, who was an American physicist and psychologist. One of the interesting things that we can take from this is a little bit of the history, and here's a quote. "I therefore take the liberty of proposing for this hypothetical new atom, which is not light, and plays an essential part in every process of radiation, the name photon." Now, the interesting part here is that he used the word hypothetical. So Lewis himself was an anti-realist with respect to what the photon is. He also said that it is not light, which is quite strange, seeing as we're trying to detect light. So he thought that it was just a mediator of force between atoms and allowed to explain their interactions. So a photon is discretized in terms of its energy levels. So if we have a cavity of length L, you have a set of discrete standing waves that can be set up in that cavity. Every single one of these modes can have a certain number state associated with it, where a photon is a discrete energy that's attributed to a particular mode. Now, when we detect light, we quite often refer to the arrival of photons as being Poisson distributed. Now, this isn't quite strictly true. There's actually a continuum between a geometric series and a Poisson series dictated by what's called the coherence time of the light. Of course, different lights have different coherence times. We know that lasers are very coherent, and of course, light from the sun is very incoherent. So how do we go about detecting light using solid-state devices? Well, there's three principal ways that we can detect these light particles. The first, a high-energy phenomena, is called pair production, where the energy of the photon is sufficient to create both an electron and a positron. As both of those have a mass associated with them, we need to have a very large amount of energy, around about 1.02 mega electron volts, or, viewed in a slightly different way, 2 times EMC squared to be able to obtain those particles. Now this obviously means that it's limited to X-ray and gamma photon wavelengths. Now Compton scattering is a slightly different phenomena where a photon is scattered by an atomic electron. Some of the energy is imparted onto that electron. The photon itself is not destroyed, but is able to pass through the material with a slightly different wavelength. Now, both of these phenomena are high energy effects. So what effect have we got left for visible, near-infrared, or ultraviolet light? And the answer is the photoelectric effect. Now, this effect comes in both an internal photoelectric effect and an external photoelectric effect. We can look back into the history of these things, and Foster-Nix in 1932 did a literature review of the light detection field, and with this quote: "We will begin with an account of the phenomena designated by Gooden and Pohl in 1920 as a primary and sometimes classified under the name internal photoelectric effect. This is to distinguish it from the so-called external photoelectric effect, i.e. the ejection of an electron from substances into the surrounding gas or the vacuum by instant light." So what is the photoelectric effect? Well, the external photoelectric effect is quite often used for photomultiplier tubes, microchannel plate detectors, where the energy of the photon is sufficient to liberate an electron from an atomic nucleus atom, but to also liberate it outside of the surface of the material, an energy gap called the work function. If we use those liberated electrons, we can use those to get an avalanche of electrons using a secondary emission process, and that's how photomultiplier tubes work. However, we're quite interested with CCD sensors, CMOS sensors, etc. So for that detection mechanism, the photon has an energy that's greater than the energy band gap of the semiconductor. It's able to bring an electron from the valence band up into the conduction band, and from there the electron is able to move through an external circuit that we can use for detection. One of the ways that we would like to detect single photon level light is to increase the amount of gain in the photodiode itself. One of the things that we can do is to use the avalanche gain mechanism. If we have a photodiode that's biased at low levels, we get unity gain. We don't get any gain at all in the device itself. If we bias it a little bit further, we can provide gains inside the device of between 10 and let's say 1,000. We can bias it even further, in fact above breakdown, in order to get gains of between 10 to the 5 and 10 to the 6. But what is this avalanche process? Well, if we have a photoelectron inside the silicon substrate, if there's a large electric field across the p-n junction, the electron is accelerated to a high kinetic energy. If this kinetic energy is greater than 1.5 times the band gap, we're able to knock other electrons out of their atomic shells. This provides a continuous exponential gain mechanism that can either be in a linear mode or a fully runaway mode. If we bias the p-n junction at the linear region, we get a constant gain with a multiplication factor given by m down here. The electron and holes both have different ionization coefficients, and this is critical when we start to look at the continuous time noise of these devices. In fact, there's an excess noise factor. If we try and minimize that, we need to arrange that the electrons have a larger ionization coefficient than the holes. If we bias the device, in fact, above breakdown by some excess bias, VEX, the avalanche current is able to quickly build up in between 10 and 100 picoseconds, and is also able to break down the PN junction almost completely. The electron flow that we get during that operation is so large that if you drop it across an external resistance, you get a voltage drop that you can then detect using a digital inverter. There's a certain amount of time that we are not able to detect photons. We call this the dead time. If we have a photon arrive at this point here, where we are just above the breakdown voltage of the device, we get a significant avalanche current that brings us up here in the IV characteristic. This large current is dropped across an external series resistance or a transistor, allowing us to drop the voltage across the device and quenching the avalanche. At some point later, we can recharge that device either in a passive mode or an active mode, and perhaps with a dead time of around about 10 nanoseconds. The dead time of single-photon avalanche diodes also dictates the maximum counting rate. If we have an active quench system, we're able to achieve a maximum counting rate of around about 1 over the dead time for a single spat. If we have a passive system, unfortunately there's a factor of E that reduces the maximum counting rate. One of the things that we can do to improve the counting rate is to have more than one diode, of course, which is this parameter here, N spads. There's been some recent work that brings down the dead time from about 10 nanoseconds down to between 1 to 2 nanoseconds. However, there's perhaps a lower limit of around about 750 picoseconds. Now, as metrologists, we could create our own device, and in fact, the Europractice system in Europe and the MOSIS system in America allows you people to have access to different foundries with CMOS processes. So for example, you might be able to design a device for TSMC, Global Foundries or UMC. Now the interesting part is all of these foundries have had either photodiodes, avalanche photodiodes or SPADs implemented in their systems. There's also been a number of industrial collaborations with respect to STMicroelectronics and Tower Jazz, both of which now offer world-class leading single-photon avalanche diodes. Now, if that's not an option due to cost or time, there's also commercial off-the-shelf opportunities. Of note, there's Hamamatsu and Sensel, both of which are collections of SPADs held in an analog kind of readout method. Philips, however, have offered a fully digital SPAD system with over 90,000 SPADs as part of the device. There's some further reading on this topic, and I would point you towards a book edited by Giurini, as well as the work of the Cova Group from the late 70s to the mid-2000s. Thank you very much.